right, and we're recording. Okay, so so last time we were talking about, I was kind of rewinding it back and talking about the fundamental theorem of calculus again, which seems like, why are we going backwards? But I think it's really helpful in the sense that it turns out that what we've been seeing with Green's theorem, right, that there's this mysteriously accumulating quantity. Circulation, boundary circulation is a mysteriously accumulating quantity, and that even though it computed on the boundary, it's actually accumulating. It's computed on the boundary, but it's actually accumulating over the interior. This kind of thing. I like to point out with the fundamental theorem of calculus, same exact thing, right? We've got this accumulating quantity. Right? Change is an accumulating quantity. It's computed on the boundary. Right? The way you compute it is by looking at endpoints only. That's the boundary. And the integrand, therefore, effectively plays the role of a density. You can even see the fact that it's a density. If you look at the formula for f prime, it's delta y over delta x. That's literally change per unit size. Right? So, a lot of analogies. I also think it's really helpful to point out that the derivative is telling you where change is happening. Right? You can see that the change is happening here. Sure, you measure it on the boundary, right? Yeah, that's how we compute the total change. But where did the change happen? The change didn't happen on the boundary. It just didn't. Right? Look at that. This is where the change happens. Right? And that derivative, that integrand in our resulting interior integral is what tells you where specifically, and furthermore, not only just where, but also how much. And that was the purpose of this example down here. You can see specifically that the derivative, by virtue of the derivative being greater at this point, right, you have an algebraic indication that there's more change happening at this point than there is at that point. Okay. So we have a theorem here in the fundamental theorem of calculus where we have an accumulating quantity that we view as being distributed over the interior, and the integrand, namely the derivative, tells you where and how much of the change that we see on the boundary is actually happening where in the interior. Okay, all right. So when I say that the same things happen with Green's theorem, it shouldn't be too big of a shocker, right? And so again, we've already talked about this, but I want to go through it again real quick. So here's where boundary circulation is detected. That's where it's computed. Right? That's where we compute circulation. But where did that circulation come from? How'd that happen? Right? What's really going on here? And the circulation happens in the interior, and we made the observation that if you had like a little leaf right there, it'd be cruising along as a result of the flow of this fluid, but it wouldn't be spinning because, it's being pushed equally on the top side and the bottom side. It's just not going to spin at all. But leaves in here, right? There'd be a lot of circulation everywhere, kind of, sort of throughout this gray area. Where, by the way, if you were to compute Green's operator would be positive in here. That positive value of Green's operator, the positive value of our integrand in our accumulation integral, right? That positive value is the indication that this is where and how much, based on the value of Green's operator, where and how much of this circulation that we see on the boundary is actually happening in the interior, and where specifically in the interior. All right, so extremely strong analogy with the fundamental theorem of calculus. Okay, and this is where we left off last time. Is everybody okay with all of this? By the way, I've hinted at the following before. Let me say it a little bit more so. I talked about differential forms very briefly when we first started off in Chapter 6 as something that we can't really talk about in this class. It's too much. It's a heavy machinery. It takes a long time to develop. It's very abstract. So it's a little bit beyond what Math 219's purpose is. But in the world of differential forms and this kind of stuff, as I'm going to present this as a cultural note, you might be entertained to notice, to know, I'll say, that in fact there is a theorem called the generalized Stokes' theorem. And Green's theorem and fundamental theorem of calculus are both special cases of that same single theorem. So the analogy between Green's theorem and the fundamental theorem of calculus is not a coincidence. It's not even vaguely coincidental. It is, well, yeah, of course they look the same. They are literally the same theorem, applied in different contexts. And we're going to see more applications of that theorem in specific contexts that are going to come up as other theorems. So anyway, all right, okay. So picking up here and proceeding. So let's see here. We have divergence. Same story, right? So remember we saw this observation here that Green's theorem, right, allows for viewing Green's operator as a density, and thus all the observations that we just made. And in the same way, the two-dimensional divergence theorem, also, same deal. You can view divergence as being a density, and therefore indicating where and how much of what you're observing, the flux that you're observing on the boundary, where and how much of that comes where in this interior. So picture example here. So I guess I'll zoom out so we can see the whole thing. If I were to talk about the boundary flux on this, this is the boundary of this interior region here, right? So this boundary that I have in purple, outward oriented, of course, that's the convention. And I can compute boundary flux. And that's where I compute it. I compute it on that boundary. Is that where it actually comes from? I say no. In the same sense that you measure change on the boundary, but that's not where the change happens. Come on, the change happens here in the interior, and the integrand tells you where and how much. Likewise, just as with Green's theorem, divergence tells you where and how much of the divergence of the flux that you're measuring on the boundary, where and how much it's happening in the interior. And I think you can probably see that by virtue of being constant over here, there's no divergence over in this yellow region because, well, it's the vector field's constant. And that constant, any partials are all going to be zero. There's no divergence happening here. Said differently, if I were to look at a little two-dimensional region here and compute the boundary flux through that two-dimensional region, you should expect to get zero. There's the exact same amount of flux going in as there is going out. Right? This is not a source of fluid, right? This is just the fluid's just passing through this region. Nothing really interesting is happening there. And then likewise over here in this region, the vector field is constant over here. There's the same amount of flux in as there is flux out in if you're looking on the right side. But if you are looking over here in the interior in this gray region here, let me pick a different color. If I were to look at a little region like that, you can see there is some inward flux, sure, and there is some outward flux, sure, but the vector field's bigger over here on the right. So there's more out and less in. And so in that region, there's going to be a positive amount of boundary flux. And this applies no matter how small you make your region. If you take a teeny tiny little region in here, and I can tell you how much of this purple flux that I'm measuring on the boundary how much of it comes from right in here? Right? And again, in the same way that Green's operator is what does that for circulation, Green's operator tells you where and how much. Well, likewise, divergence is what tells you where and how much when you're talking about flux. So we would find if we computed divergence in this picture, in this region, the divergence would be 0. In this section over here, divergence would be 0. And in this section in here, divergence would be positive. So where does this flux come from that we measure on the back? It's coming from where the divergence says it's coming from. It's where the divergence is positive. Yes?
I'm a little bit confused about the arrows on the boundary.
Yeah, that's just indicating, I'm just describing that, when I say flux here, keep in mind we have these conventions about orientation. And what we call positive flux, we need to have this idea of which direction is positive and which direction is negative. So these outward arrows are just indicating what the orientation is, namely specific. What am I considering the positive direction for flux? So looking over here at this left edge here, right? The orientation, the positive direction for flux is this way, but I've got fluid flowing through that edge going the opposite way, and that's why I say there's negative flux happening on the left side. And then over here on the right side, the fluid is going through this edge in the direction that we call positive by virtue of these purple arrows. So that's where positive flux is happening. Is that cool?
Yeah, but does that mean a boundary when you're measuring fluxes has a different definition than a boundary when you're measuring?
Yeah, that's right. The conventions on orientation depend on what you're computing.
Okay.
That's right.
The whole left hand thing.
Yeah, that's right. It's just different. If you're talking about flux, then the convention is outward. If you're talking about circulation, then the convention is move in the direction so the region's on your left. Yep. Okay. All right. So let's see a numerical example. We got a vector field, and this vector field here, I hope it comes as no surprise. This vector field, if you look at a rectangle, you can talk about how much circulation there is or how much flux there is. And we don't even need to compute what those quantities are. Certainly you'll agree that there is going to be some amount. You get an answer if you compute the circulation, and you'll get an answer if you compute the flux. So those quantities, where is it really coming from and how much? In particular, I want to compare these 2 points here, 3,3 and 2,4. Right? And is there more circulation coming from 3,3 or is there more circulation coming from 2,4? Easy computation. If you want to know about circulation, you look at circulation density, aka Green's operator. Right? Punch it up with the partial derivative formula. This is what you get for Green's operator. And by virtue of Green's operator being greater there, then you have more circulation coming from that point 2,4. Green's operator just tells you so. All right. And then now analogously, if you want to talk about where's the flux coming from, well, flux, if we want to understand flux, you look at flux density at these 2 points, aka divergence, aka this formula right here. And again, it's computed with partial derivatives directly from the vector field. And where is it greater? Well, that's the greater of these 2 divergences that I computed. And so so at the point 3,3, that's where the flux density is greater. And said differently, this is where more between these 2 points, 3,3 is contributing more to this boundary flux that I might have computed than 2,4 is. Okay. Yeah.
Could you also use the magnitude of the curl of that to find which position has greater circulation?
So the problem, it's a great question. The problem is the way I've defined curl, this is back in chapter 3, it's only defined for 3-dimensional vector fields. Yeah. Now you'll recall that when we wrote down Green's theorem, one of the notations that I wrote down, unenthusiastically was curl. Right? So this is, if you want to choose that terminology, then then it's literally the same thing as Green's operator. Right? It's this formula right here. I prefer reserving one term to describe the one thing, and then the very different concept where we talk about three-dimensional. I mean, curl in 3 dimensions really is very different, and I just don't like blurring those. It's just a notational choice, though. Yeah, good question. Okay, all right, where are we going? Here we go. No, here we go. All right. Yeah. Okay, so moving along. By the way, you may have noticed I went ahead and put section 6.2 on the lecture schedule as having been completed on Friday, even though I didn't finish this last little bit of stuff that we just talked about. And I did that because this last little bit of stuff we just talked about shouldn't have been relevant for any homework exercises, I don't think. And so I didn't want to delay y'all from getting started on those homework exercises over this 10-minute discussion here that we just did that shouldn't have been necessary for those exercises. So now we're done with 6.2. Okay, section 6.3. This first theorem I'm going to start with here is not the one that the book starts with, so I'm taking a slightly different point of view. We're going to get all the same stuff done, but I just like doing it in this order. It's called the fundamental theorem of line integrals. You'll see why seconds from now when we state the theorem. Fundamental theorem of is just like the fundamental theorem of calculus, except it's for line integrals. So here it is. There you go. Line integral is computed f of b minus f of a. It looks highly familiar, right? The catch is that this vector field has to be the gradient of the function that you use to evaluate on the right-hand side. Now, if this were the fundamental theorem of calculus, this wouldn't be gradient, this would be derivative, right? So, gradient's kind of a derivative, though. So, I mean, it's really just the... I'll say this, if I were to ask you to, write down a wild speculation of what you think the fundamental theorem of calculus would look like, but for a line integral, I'll bet you this is what you would have written down, right? It's extremely analogous. Anyway, there it is. And there's different ways you can think about this. The most efficient way that I know to prove this result is not the one I'm going to show you, because even though it's efficient, I feel like it leaves out the point of view. And I think the most valuable point of view to have is this is the one I'm going to talk about. So I'm going to view this as being an accumulation theorem, just like Green's theorem, just like the two-dimensional divergence theorem, just like the fundamental theorem of calculus. Right? So we're going to take the same point of view that we're going to identify an accumulating quantity, and then we're going to write it as an accumulation, and then rewrite in terms of a density and theorem. Okay, so first, the quantity in question, change, is an accumulating quantity. Now, I claim that change is an accumulating quantity. Here's how you can see it. If you have a curve and you ask how much did f change across this curve, right? And then if you ask, okay, well, yeah, but if I were to just compute the change across this little piece of curve, and then separately, if I were to compute the change across that piece of curve, would this change plus that change, would that give me the change across the union, the change across the, the pair of them together? Is the whole the sum of the parts for this quantity? And yeah, absolutely. And here's how the algebra works out. If you look at this interval here, keep in mind the formula for change. You have positive of the endpoint and then negative of the starting point. And so across this first piece of curve, we'll have a positive term for the value at x1 and a negative at the value of x0. For this second interval, I was going to highlight There's the change on the green piece of curve. Now on this blue piece of curve, positive at the right end, at the end point of that piece of curve, negative at the starting point. That gives us that. And then notice the value of f at x1 appears twice, but with opposite signs, and so it cancels. And you can see that right there in the algebra. The x1, the f of x1s just cancel. Everybody with me? So, I mean, again, it's kind of like what we saw with Green's theorem. With Green's theorem, when you slice all those little pieces of edge that you create in your slicing process, well, that's part of the, you got two different orientations on each side of it, and the opposite orientations make it cancel. Well, same thing here. I did a snip, right? Kind of a one-dimensional version of a slice at this point, and well, that's the end point for this green piece of curve. It's the start point for the blue piece of curve, and so opposite signs and they cancel. So it's really, really analogous. It's just like Green's theorem so far in that sense. Okay. All right. So as a relatable physical example, you can think about this as talking about how altitude accumulates. Right? Change in altitude accumulates as you drive along a mountain road. If for the first 10 minutes of your drive, you gain 100 feet of altitude, and for the following 10 minutes, you gain 200 feet of altitude. Well, then for those 20 minutes, you gain 100 plus 200, namely 300 feet of altitude. It just adds. Of course it does. Okay, next, what is the corresponding notion of density? Well, if you move from there to there, and if you want to know how much does a function change as you move from there to there, said differently, as you displace by a vector dx, right, that change is computed by this old formula from chapter 2, right? Output change relates to input change by way of dot product with the gradient. This is the real value function. Everybody happy with that? Okay. And then I'm going to rewrite because dx can be rewritten as TDS, and then you can move parentheses around a little bit. And now if we look at this version of what I've got, then you see gradient f dot t is what you multiply by the size, ds, the size of that little piece of curve. Right? Now that doesn't account for any orientation or anything, but that's just the length of that little piece of curve, right? And tells you how much change there is for that piece of size. And of course, what is a density? Density is change per unit size. Yeah? So, the density is that, gradient dot t. Everybody all right? Okay, so, I'm gonna come back to this other stuff in a second, but let's go ahead and spike the football here. Change is an accumulating quantity. Grand total change is the sum of the little pieces of change across the entire curve. And on any little piece, how much change happens on a little piece? Well, we just computed that up here. Change on any little piece is that. And so, theorem. Right, there's our fundamental theorem of line integrals. F of b minus f of a, aka change, is that interval. Which I'm going to real quick. I'm going to rewrite that. Rewrite that as TDS is dx. And here's the way we maybe more commonly think about it. Integral dot dx. Did I see a hand somewhere? Yes.
Yeah, do you mind just explaining again why change is the gradient times the dx?
Oh, yeah. So this is just an old formula we didn't write it in exactly this notation. I didn't use delta to represent change, but I think maybe we wrote it as df. right? And input changes and output changes are related by derivatives. And when you have a real valued function, dot product of the gradient is the... Yep, that's all. Okay, so let me talk about this oriented density business. This is weird. So let's look first at this formula, and we call this the density because it's what relates input change to output change. And what specifically, though, I think about change. I think of this as being a measure of size that's scalar. It's how long is that piece of curve. So what I want to do now is be a little bit more flexible with our use of the term density, and we've already kind of expanded, made more flexible our idea of the term density. Right? You come into this class perhaps thinking of density as being literally mass per literally volume. It's got to be mass per unit volume. That's what they taught me in high school, right? That density is mass per unit volume. And then I generalized that, and I said, well, it doesn't have to be mass. What if it's some other quantity? Population or whatever, right? So we became open-minded that, hey, the quantity could be any sort of accumulating quantity. And then we became open-minded also that denominator, size, well, it could be volume, but it might also be area. It might also be length, right? Any appropriate notion of size to the context. And what I want to do now is extend our open-mindedness and our flexibility a little bit more. Why should our size have to be a scalar notion of size? In some contexts, and this is it, mightn't it be more convenient to think of what you might call an oriented size? Right? It's just size. The dx vector, its magnitude is the size. Right? It's just also got an orientation aspect, pointing in a certain direction. And hey, I don't know, maybe that'll be useful at some point. And in fact, it is, as you see from, this formula. Right? This formula shows that the gradient, that thing there, that is a relationship between size, oriented size, if you will, right, and this accumulating quantity. So if you want to talk about quantity per unit size, okay, fine. But if you want to talk about quantity per unit oriented size, right, then that's a reasonable interpretation to make of the gradient. And so since we're looking at an oriented notion of size, I think it's reasonable to call this an oriented density. So basically, it's just, we know that vectors are useful. We know that vectors are really kind of the natural way to write things down. And translating the equation to what we have over here on the far right, I got to make this a scalar because that's got to be a scalar. And, trying to cram it into this scalar point of view, yeah, sure, fine, but isn't it convenient to just leave it in the vector point of view? And all we have to do to make sense out of that is just, again, be a little flexible. And we've got these two new concepts here. We have the idea of an oriented size, so sort of a point of view on what a vector is, and an oriented density that comes along with it. So that's all that is. The reason I spend some time on this is that this is really going to come up in a big way when we get into Chapter 7, when we talk about something called Stokes' curl theorem. And this idea of an oriented density is going to be a big deal at that time. So this is a little bit of, I'm kind of laying some groundwork here. All right. Are we doing all right? All right, so that was a little bit of a digression. We've got a brand new theorem. We haven't used it yet. Let's go ahead and do our very first example with the fundamental theorem of line integrals. Notice that this example, by the way, does not announce itself as a fundamental theorem of line integrals question. The question just says, hey, I compute this line integral. And so, golly, how are we going to compute this line integral? We have various tools for computing line integrals. we could take our parameterization, which is given to us, right, and we could plug and chug. Or we could entertain the possibility of using Green's theorem. Green's theorem is a fantastic theorem for computing line integrals sometimes, right? There's a catch. Green's theorem only works if the curve in question is a closed curve. It's got to be a closed curve. So, maybe it works sometimes, and sometimes it just doesn't apply. There's a catch to using the fundamental theorem of line integrals as well. Notice, again, I made a thing about this already, but the vector field of which you are taking a line integral has to be a gradient. Non-negotiable, right? Not only does it have to, this is not sort of, mathematical formalities. It's got to be a gradient, if only for the fact that the thing that it's the gradient of plays a massive role in how to compute the right-hand side. I need to know this anti-gradient to even be able to use the right-hand side. Right, so again, it's not that the right-hand side is unequal to the left, if f isn't a gradient. It's that there is no right-hand side. There's no theorem at all if f isn't a gradient. All right, is everybody with me? So again, highly important, right? This is very important that you have to confirm that you only use this theorem if your vector field is a gradient. All right, so all right, is our vector field a gradient here? Is this a gradient? Fingers crossed. Well, yeah, it is. Check it out. It's a gradient of this function here. X squared, y squared. Easily confirmed. Everybody on board? So we've got here our anti-gradient. X squared, y squared is our anti-gradient. And so that's what this f function is. And now all you got to do is plug in the endpoints. Okay, to be fair, you do have to, take your starting value of t and plug in and see what your starting point is. Right? So that's your starting point. It's where t equals 0. For this example. And then you do have to see where your ending point is. Well, let's see, we end when t is equal to pi, so you got to plug that in, and that gives you the ending point b. A little bit of arithmetic to find those starting and ending points. But then, you plug in the starting and ending points into the anti-gradient, f of b minus f of a, and this integral we were asked to compute, namely an integral of a gradient. We can use the fundamental theorem of line integrals, and f of b minus f of a gives me 0. Lucky. Nice arithmetic, worked out well. How we doing? Everybody happy? Yep.
So we would know to use the fundamental theorem if it immediately jumps out at us that it's a gradient?
So you ask a great question. There are some things about how to diagnose and realize, which theorem should I use, that I'm not going to be able to talk about until we get a little bit more done. But in this case, yes, certainly you need to know that there is an anti-gradient. But how does one identify the thing? How does one find the anti-gradient, right? Or said differently, what is it about this that made me realize that there is an anti-gradient, right? This is a tough question. And there's some tricks to that. One of them we have already seen, actually. And that is, we've already talked about how, being a gradient is the same as Green's operator being 0. Y'all remember that from chapter 3? It was a quick. We have these diagrams that are exact. What we call exact diagrams. A lifetime of 2, right? Everything is a lifetime of 2, and so that is a test that you can do. So you can take the x partial of this and the y partial of that and subtract and see. Oh my God, 0. Green's operator is 0. It died. That means it came from previously. Yeah. And I'm going to talk more about that specific point a little bit later. All right. Yeah, so there's an example. All right. Now here's what the book starts with, this idea of path independence. And it's not immediately clear how this relates to the fundamental theorem of line integrals. So think of this as a new topic. And I start off with a seemingly painfully obvious statement. The value of an integral depends on the domain that you compute it on. Well, of course it does, right? You're adding up a bunch of values of a function. Which values you're adding up matters. It's one of the, it's just a seemingly ridiculously obvious statement, and of course it's very true. Absolutely. What's not obvious is this next sentence. There are some vector fields. There are very special vector fields that we're going to define in a second. These are called path-independent vector fields, where, shockingly, only the endpoints matter. I would say it seems implausible, right? Look, it says right here I'm computing an integral over a curve. That means I'm looking at the value of the function at all of the points on the curve, and as you look at different points you really have to go along the curve to add up the values of the function along the curve, and you're telling me that I could take any other curve? As long as the endpoints, right? All the endpoints matter, right? But some other curve between those endpoints could give me the same value for the integral? Seems ridiculous. But I claim that this is a thing. And here's the definition. A vector field, let's see here. A vector field is path independent. If whenever you have any two curves, C1 and C2, that share the same starting and ending point. So maybe they both start there, maybe they both end there. The green curve maybe is like this. The blue curve is maybe like that. Right? This green curve and this blue curve, they start and end at the same points. And I'm saying there are some vector fields, what we call path-independent vector fields, that say, okay, well, these line integrals have to be equal, even though the curves are almost entirely different. Yes?
Why is it only some vector fields if every time we're only using one point?
Because even with the restriction that we're comparing only curves that share the same starting and ending points, even with that restriction, most vector fields do not have this property. So it's still only the special vector fields, what we call path-independent vector fields, that have this property. There's plenty of vector fields, not path-independent, where, the green integral is totally different from the blue integral. Yeah, absolutely. Is that satisfying?
Yeah.
Okay. Everybody else all right? Okay. Okay, so first I want to try to persuade you how rare this is by taking an obvious, I don't want to say counterexample, but an obvious example of what you would expect. Namely, here's a couple of curves that have the same starting point and ending point, right? They both go from the origin to 1, 1. And let's just kind of think through what the values of these integrals are, and shocker, we're going to get different answers. Of course we're going to get different answers. They're different curves. Why would we expect them to be the same, right? But along in here, the value of the vector field is 0. So there's no line integral on that green segment. Along in here, the vector field's not 0, but the vector field's pointing up. The curve is going to the right, and that dot product is 0. So on the green curve, we definitely get 0. On the blue curve, we have this orthogonality issue along the bottom, right? There's definitely, the curve is going that way, the vector field is that way. That's perpendicular. There's no line integral along that bottom piece. But as you go up here, the curve is going up, the vector field is going up, the vector field is not 0. We've got a positive amount of line integral on that blue curve. So this example is, by the way, this is the norm. This is what happens with most vector fields, right? To your question, right? Most vector fields start and end at the same point. Yeah, so what? I need to actually look all the way along the curve. So of course you should expect to get different values. And again, here you go. So again, this is the purpose of this example is to make it clear that we shouldn't expect path independence. And yet, sometimes path independence happens. In fact, it happens shockingly often. And here's my main example. Gradient fields. Gradient fields are all path independent, believe it or not. All gradients. And easy to see because let's play the game. Here's a starting point and an ending point that we're going to fix. Right? And then we're going to look at, on the one hand, there's this curve from A to B. And then there's this curve from A to B. And again, now with this example up here in mind, we would expect to get different values, right, for these two different curves. But comparing, this line integral to this line integral, again, you expect to be totally different. Keep in mind, because my vector field is a gradient, right? This vector field here is a gradient. That means I can write down the fundamental theorem of line integrals. And the fundamental theorem of line integrals says that I can compute that integral by looking only at the endpoints. Namely, it's f of b minus f of a. And I can compute this line integral by looking only at the endpoints, f of b minus f of a. And, well, we got the same a and b. Same a and b. And this vector field, whatever its anti-gradient it is, it is what it is. Same in both calculations. And so these two integrals, because of the fundamental theorem of line integrals, these two integrals are both equal to the same other thing, and therefore they're equal to each other. Everybody see how that worked out? So, it's the weird thing about path independence is, you look at the definition and you say, come on, get out of town. And then you look at this example and you're like, right? Come on. Obviously, it depends on where you go as to what the value is going to be. And this was my intuition for a long time. And then you make the realization, here's an entire category of vector fields for which, of course it's path independent. Fundamental theorem of line integral makes them path independent. That's right. How are we doing? And again, I have forgotten to turn my phone on. I'm sorry. Okay. Why am I bothering to erase that? That's fine. Okay. So it also works the other way. So what we've shown up here is that if you have a gradient, then it's path independent. It also works the other way, that if you have a path independent, you need regularity, you need continuity. Let's not worry about that. But if you have a path independent vector field, it's also a gradient. So regularity issues aside, again, not what we're focused on in this class. Gradients and path independent vector field, these are the same vector fields. All the same ones. Again, as long as no regularity problems. Okay, how are we doing? Okay. All right. So now here's a different way to think about path independence. This is a useful point of view that's going to come up in a few minutes. But we've talked about how, we've got this curve and we've got this curve that start and end at the same point. And I make the observation that if you have two curves starting and ending at the same point, then between the two of them, they kind of define a loop. They define a closed curve. How about that? Right? So if we know we have a path-independent vector field, then this is equal to that. That's what path independence means, that these two integrals have to be equal. And then just kind of subtract this one over to the other side. And altogether, that tells you that the integral on C1 combined with, let's see here, it's along C2, but wait a minute, I'm going backwards along C2. And so we really have integral on C1 and then minus the integral on C2. Right? And so the integral on this orange curve, this closed orange curve here, is 0. Does that make sense to everybody? Right? We know that these two things are equal, therefore this difference is equal. That's just arithmetic. And if that difference is equal to 0, well, of course, that difference is the orange line integral, so that means that orange line integral is 0, and vice versa. So here's your alternative formulation. Path independence means that all closed line integrals are 0. How we doing? Okay. All right. Here's an example of this. I want to consider a vector field that represents what I'm going to call steepness. Right. So if you're on the side of a mountain or a hill or what have you, wherever you might be happening to stand, you can talk about the vector field describing which way is uphill and how steep is it. Right, so this is what I'll call the steepness vector field. And of course, we already know what the steepness vector field is. It's the gradient of the altitude function. Right, chapter 2 discussion. Okay, well here's the thing. It's a gradient. That means that it's path independent. Right, we just got through observing that gradients are path independent. Path independent we can reformulate as saying that closed line integrals are 0. That was the most recent point that we just made. And so let's think about what this is really telling us. What this is telling us is that if you're going around a closed curve, right, starting and ending at the same point, and if you're keeping track of how much altitude is changing, right, that's what this integral does, is how much is h, aka altitude, changing. Grand total, if you start and end at the same point on a hike, your total altitude change is 0. Because you literally came back to the same point that you started, where you have exactly the same altitude. And so, well, of course you have 0. So, I like to think of this as a kind of a mathematical representation of the obvious point, what I'm going to call here Escher stairs. This is a famous old drawing from a long time ago. I don't remember exactly, but M.C. Escher painted a lot of optical illusions in his art, and this one makes it look like these people here they're walking up the stairs, and then they turn right, and they keep walking up the stairs, and then they turn right again, still walking up the stairs, and then here they go, and they still going up, and yet somehow came right back to where they had been. That's mysterious. Right? It seems weird. And obviously impossible, and the obviousness of this being impossible is expressed by this math there. All right? Everybody all right? Okay. All right. Okay. Okay, let's see how we're doing. Oh, we have 1 minute left. Gosh. You know what? This is a pretty good place to draw the line. We'll draw the line right there and pick up here on Wednesday. Hope you all have a good start to your week, and see you later.